All right, hello and welcome back. It's your boy Hank Hackerson at Hank Hacks Hackers, and we are continuing down our security engineer pathway. This would be episode 3, day 3, and we're going to be talking about introduction to cryptography. That rhymes. And yeah, so this is going to be our outline for today. We're going to be talking about the intro, obviously, symmetric encryption, asymmetric encryption, the Diffie-Hellman Key Exchange, hashing, PKI, SSL, TLS, authenticating with passwords, and cryptography and data example. There is some task files that we can use and play around with. And yeah, that's about it. If you are studying for your ethical hacker, pen tester, security engineer, cybersecurity analyst, any of those certifications, I encourage you to like and subscribe and turn on the notification bell so that you get notified the next time that a video comes out, because all we talk about on this channel is cybersecurity, pen testing, ethical hacking, security engineering, and the information on this channel will actually be directly applicable to your studies when you go and take your examination, certification exams, or that'll be directly applicable to your day-to-day job as a security engineer or a pen tester, ethical hacker, so on and so forth. So I do encourage you to subscribe and turn on notification, and it would just be really awesome to have you as a part of our community. And I do respond to all the comments that come in to just make sure that you get anything that you need to make sure your education is complete. So it would just be amazing to have you as a part of our community. So without further ado, let us get into the introduction of the room. The purpose of this room is to go through basic cryptography. So symmetric encryption such as AES, asymmetric, which is RSA, and these are obviously just examples. We have the Diffie-Hellman or Diffie-Hellman Key Exchange, hashing, and then PKI. So let's kind of look at a general concept here. So suppose you want to send a message that no one can understand except the intended recipient. So what do? Right? You need to create some kind of a cryptography. One of the simplest ciphers is the Caesar cipher, and it's more than 2,000 years old. And the Caesar cipher shifts the letter by a fixed number of places to the left or to the right. So if we look at shifting by 3 to the right to encrypt, then it would look like this. So the letter A would end up being the letter D, right? And then when you decrypt it, you take the letter D and then you assume that it's an A, right? So it goes 3 to the right to encrypt it, and then to decrypt it, you would go 3 to the left. That's basically the most basic form of encryption, which is the Caesar cipher. And then we have the TryHackMe word. If we wanted to encrypt it using the Caesar cipher, we would get this. So WUB. So since Y is already at the end of the alphabet, if you just go another 3 to the right, you would end up at B, right? So WUBKDFNPH ends up being TryHackMe when you decrypt it. It uses a key between 1 and 25 with a key of 1. Each letter is shifted by 1 position when A becomes B and then Z becomes A. With a key of 25, each letter is shifted 25 positions. So A becomes Z, B becomes A, etc. A key of 0 means that there's no change. So a key of 26 will also lead to no change. And A will become an A because it just goes through 26 places and it ends up back where it was. Consequently, we conclude that the Caesar cipher has a key space of 25. There are 25 different keys that you can choose from. Consider the case where you have intercepted a message with the Caesar cipher, and this is what the message is. And now we have to decrypt it without the knowledge of the key. And we can attempt this by using brute force. We can try all the possible keys to see which one makes most sense. And in the following figure, we notice that the key being 5 makes the most sense. So this being going back 5 places, going to the left 5 places, would end up being T, and then M would be H, N would be I, so on and so forth. So this is Alpha Bravo contacting Tango Hotel Mike, right? And this is Alpha Bravo AB contacting THM, right? TryHackMe Tango Hotel Mike. And that's what it looks like. And this is just a version of this thing where you go through the iteration. So if there's 1 as the key, meaning you only go 1 place to the left, you would end up with XLMW. If you go 2 places, you end up with WKLV, VJKU, UIJT, and then TIHS. Oh, that makes sense. That makes sense, so on and so forth. So the Caesar cipher is considered a substitution cipher because each letter in the alphabet is substituted with another. Another type of cipher is called the transposition cipher, which encrypts the message by changing the order of the letters. And we can do a simple transposition cipher in the figure below, where we start with the message, "This is Alpha Bravo contacting Tango Hotel Mike," and the key is 42351. After we write the letters of our message by filling one column after another, we arrange the columns based on the key and then read the rows. In other words, we write the columns, we write by columns and we read by rows. Also notice that we ignored all the spaces in plain text in this example. The resulting ciphertext would be something like that, right? Is read one row after another. In other words, a transposition cipher simply rearranges the order of the letters, unlike the substitution cipher, which substitutes the letters without changing their order. So we have column 1 would be this, is, etc., and then you change the formatting of it. So this is Alpha Bravo contacting Tango Hotel Mike, right? So if we were to encrypt it, it would be done so this way. So 42351 takes placeholder number 4, puts it in the first place. Placeholder number 2 stays, 3 stays, 5 now comes to place 4, and then 1 takes the letter from the first box right here, right? So you see how they kind of switched it, right? So 1, 2, 3, 4, 5, and then you have 4, 2, 3, 5, 1, and that's how you mix it all up. And it just goes ahead and does that for you. It does literally the same thing for the next one and the next one, and we end up with Tango still being here because 4th place actually has the word Tango in it. So all of these, some of these actually end up making sense. This, so on and so forth. I mean, whatever a completed word is inside a specific column still will make sense. It's just that it's now kind of messed up a little bit, not really, but it's been, what is the word here? Transposition is what it's done. It's been transposed. The plain text is this. The ciphertext ends up becoming this, right? Because you're still going down the path right here. You're still going down the column. When you read it, NGTA, NGO, and it ends up turning into this. Oh, actually, no, you know what? They're not even reading. They're reading it also this way. So NPCOT, NPCOT. So that's what happens when you encrypt it. So you read it downwards when it's not encrypted. When it is encrypted, it's read this way. And so this is very interesting. And I wonder if it's all, I don't think it's all 1, 2, 3, 4, 5, and then with however many rows that this is, I'm pretty sure it gets more complex as you do that. This task introduced simple substitution and transposition ciphers and applied them to messages made of alphabetic characters. For an encryption algorithm to be considered secure, it should be infeasible to recover the original message, which is the plaintext version. In mathematical terms, we need a hard problem, a problem that cannot be solved in polynomial time. A problem that we can solve in polynomial time is a problem that's feasible to solve even for large input, although it might take the computer quite some time to finish it. If the encrypted message can be broken in 1 week, the encryption used would be considered insecure. However, if the encrypted message can be broken in 1 million years, the encryption would be considered practically secure. Consider monoalphabetic substitution cipher, where each letter is mapped to a new letter. For example, in English, you would map A to one of the 26 English letters, then you would map B to one of the remaining 25, then C to the remaining 24, and so on. For example, we might choose the letters in the alphabet A through Z to be mapped out to be X, P, A, T, yada, 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 respectively. In other words, A becomes X, B becomes P, and so on, and the recipient needs to know the key, which is, this is the key, right, to decrypt the encrypted message successfully. This algorithm might look very secure, especially since trying all the possible keys is not feasible. However, different techniques can be used to break a ciphertext, such as an encryption algorithm. One weakness of such an algorithm is letter frequency. In English text, the most common letters are E, T, and A, as they appear at a frequency of 13%, 9.1%, and 8.2% respectively. Moreover, in English text, the most common first letters are T, A, and O, as they appear at 16%, 11.7, and 7.6 respectively. Add to this the fact that most of the message words are dictionary words, and you will be able to break an encrypted text with the alphabetic substitution cipher in no time. We don't really need to use encryption key to decrypt the received ciphertext, UYVSXD, etc., 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 as shown in the figure below, using a website such as Quipcube. We'll take it a moment to discover the original text was. The man who moves a mountain begins by carrying away small stones. This example clearly indicates that this algorithm is broken and should not be used for confidential communication. I love this freaking quote right here. The man who moves a mountain begins with carrying away small stones. That is brilliant. So QIP, and that's what it is. So you should put the puzzle in here. I don't think they even gave it a clue, and it just did the decryption for us. So that's very cool. So you've viewed the reviewing message. We're going to use the tool itself. So I'll take this whole thing and go paste it inside of Quip Pro and see what we can find. Or not Quip Pro. It freaking took the entire thing away. So let's solve it. Today is victory over yourself of yesterday. Tomorrow is your victory over lesser men. Miyamoto Musashi. There it is. This is a very cool website. I love this. This is cool, man. I love this shit. So we are now here, and let's take this. Oh, Miyamoto Musashi is all I need to find here. So I'm just gonna delete the first part of that. There we go. And we got it. That was the first task. That was really cool. That was the intro. So I can only imagine how much cooler it ends up becoming. So that was the intro of the introduction to cryptography. Symmetric encryption. So these are the key terms here. So we have cryptographic algorithm, or the cipher, and it defines the encryption and decryption processes. The key is the algorithm needs a key to convert the plain text into ciphertext, and then vice versa. And then the plain text is the original message that you actually want. You get to see. Ciphertext is the message that the message in its encrypted form. And so a symmetric encryption algorithm uses the same key for the encryption and the decryption, and the communicating parties need to agree on a secret key before being able to exchange any messages. In the following figure, the sender provides the encrypt process with the plain text and the key to get the ciphertext. The ciphertext is usually sent over some communication channel. So the sender has the plain text that gets encrypted, there's a key, and then there's the ciphertext that gets sent out. And then that gets transferred. And then the ciphertext comes back and it goes through the decrypt process using the same key, and then the recipient ends up getting the plaintext version of that message. The National Institute of Standard and Technology, which is NIST, published the Data Encryption Standard, DES, in 1977, and it's a symmetric encryption algorithm that uses a key size of 56 bits, which is, in these days, it's not that big of a deal. In 1997, a challenge to break a message encrypted using DES was solved. Consequently, it was demonstrated that it had become more feasible to use a brute force search to find the key and break a message encrypted using DES. In 1998, a DES key was broken in 56 hours. These cases indicated that DES could no longer be considered secure. NIST published the Advanced Encryption Standard, AES, in 2001. Like DES, it's a symmetric encryption algorithm. However, it uses a key size of 128, 192, or 256. And as you can imagine, the higher it goes, the more secure it becomes. But it's still considered secure and in use today. It repeats the following 4 transformations multiple times. So sub-bytes on the state, shift rows state, mix columns state, and add round key. So sub-byte looks up each byte in a given substitution table, the S box. This is starting to get technical, so I'm gonna read slower instead of just zooming through everything. So sub-bytes looks up each byte in a given substitution table, which is the S box, and substitutes it with the respective value. The state is 16 bytes, which is 128 bits, so you just multiply this by 8. Saved in a 4x4 array. Shift rows, the second row is shifted by 1 place, the third row is shifted by 2 places, and the fourth row is shifted by 3 places, and this is shown in the figure below. And we have mixed columns. Each column is multiplied by a fixed matrix 4x4 array, and then we have add round key, which is a round key is added to the state using the XOR operation. So a lot of stuff happening here. So we have the input that is being shifted by 1, it seems like. Then you have shift rows that is being shifted by however many this is right here. It seems like each row is being also shifted by 1. I don't know if we're going this way. So we're going counterclockwise. So yeah, the rows are being shifted by 1 still. And the output ends up looking like this. So S00 still, S00 still. S11 now comes down here. S22 now comes down and becomes the column again. S33 is now all the way down here. So this is what it would look like if we took this and then we just shifted them all to be in that first column. And then all of the following columns are going to follow along, right? So this would be S00, so this is S01, this is 11, so that's 12, 22, 23, 33, 30, right? Because it's going back and restarting. The total number of transformation rounds depends on the key size. Don't worry if you find this cryptic, because it is. Our purpose is not to learn the details of how AES works, nor to implement it as a programming library. The purpose is to appreciate the difference in complexity between ancient encryption algorithms and the modern ones. If you're curious to dive into details, you can check the AES specifications, including pseudocode and examples in its published standard, which is the FIPS Pub 97. It keeps opening it in the same freaking window, and I'm trying to open it in a different window. So let's go back down here, and this is it right here. So there you go. That opened it up in a new window now. And we can, it's fairly short, so I'm still not going to read it, but FIPS Pub 197, that's what it is. So in addition to AES, many other symmetric encryption algorithms are considered secure, and this is a list of those things supported by GPG, which is GNUPG 2377, for example. Encryption algorithm, AES 192, 256, IDEA 3DES, CASTS, Blowfish, Twofish, Camellia 128, 192, and 256. So AES with a key size of 128, 192, 256. IDEA is the International Data Encryption Algorithm. The 3DES is Triple DES Data Encryption Standard, and it's based on DES. We should note that 3DES will be deprecated in 2023 and disallowed in 2024. So this is pretty much out the door already. Also known as CAST 128. Oh, this is not CASTS, it's CAST 5. Also known as CAST 128. Some sources state that CASE stands for the names of its authors, Carlisle Adams and Stafford Tavares. Designed by Bruce Schneier is Blowfish, designed by Bruce Schneier and derived from Blowfish is Twofish. And then Camellia, designed by Mitsubishi Electric and NTT in Japan. Its name is derived from the flower Camellia japonica. All the algorithms mentioned so far are block cipher symmetric encryption algorithms. A block cipher algorithm converts the input, the plain text, into blocks and then encrypts each block. A block is usually 128 bits. In the figure below, we want to encrypt the plain text Tango Hotel Mike, a total of 16 characters. The first step is to represent it in binary. If we use ASCII, T is 0x54. In hexadecimal format, A is 0x41 and so on. Every two hexadecimal digits constitute 8 bits and represent 1 byte. A block of 128 bits is practically 16 bytes and is represented by a 4x4 array. The 128-bit block is fed as 1 unit to the encryption method. So all of these things are individually encrypted, and this represents the plain text, but this is fed as 1 block, and that goes and becomes encrypted. And then this is what it turns into is the ciphertext right here. So Tango Hotel Mike, which is 5141 4E, etc., etc., etc. This turns into this 5441, my bad. So 5441 4E 47, etc. So that turns into that for the plain text ASCII. That's what they're. So this is the ASCII version of that. And then this is going to go get encrypted, and it's going to turn into ciphertext. And so it would turn into that in this case. If we look at another symmetric encryption, which is stream ciphers, which encrypt the plain text byte by byte. Consider the case where we want to encrypt the message Tango Hotel Mike. Each character needs to be converted into the binary representation. If we use ACT is 54 again in hexadecimal, while A is 41. And the encryption method will process 1 byte at a time. This is represented like this. So you send a message in still, and it goes 1 byte at a time. 54, 41, 4E, 47, 4F, and it gets encrypted, and it comes out like this. So instead of it being this whole thing right here, it gets encrypted 1 piece at a time. Symmetric encryption solves many security problems discussed in the security principles room. Let's say that Alice and Bob met and chose an encryption algorithm and agreed on a specific key. We assume that the selected encryption algorithm is secure and that the secret key is kept safe. Let's look at what we can achieve. Confidentiality, integrity, and authenticity, the CIA triad. So if Eve intercepted the encrypted message, she wouldn't be able to recover the plain text. Consequently, all messages exchanged between Alice and Bob are confidential as long as they're not sent encrypted. The integrity, when Bob receives an encrypted message and decrypts it successfully using the key that he agreed upon with Alice, Bob can be sure that no one could tamper with the message across the channel. So it maintains its integrity, right? When using the secure modern encryption algorithms, any minor modification to the ciphertext would prevent successful decryption or would lead to gibberish as plain text. And then authenticity, being able to, and it's supposed to be availability, not authenticity. So confidentiality, integrity, availability is the actual CIA triad. In this case, they're using authenticity. Being able to decrypt the ciphertext using the key also proves the authenticity of the message because only Alice and Bob know the secret key. So this is not the same as the regular CIA triad. It starts the same, but it ends different. We are just getting started, and now we know how to maintain confidentiality, check integrity, and ensure the authenticity of the exchange messages. More practical and efficient approaches will be presented later. The question for now is whether this is scalable, okay? So with Alice and Bob, we needed 1 key. If we have Alice, Bob, and Charlie, we need 3 keys. 1 for Alice, 1 for Bob, and another for Alice and Charlie, and a third for Bob and Charlie. However, the number of keys grows quickly. So if you have between 100 users and it requires 5,000 different keys, if you're curious about the mathematics, that's 99 plus 98 plus 97 all the way down to 1, and that's 4,950. Moreover, if one system gets compromised, they need to create new keys to be used with all the other 99 users. Another problem would be finding a secure channel to exchange the keys with all the users. So this quickly gets out of hand. In the next task, we're going to cover asymmetric encryption, where one of them gets a private key and the other one gets a public key. One of the problems solved with asymmetric encryption is that when 100 users only need to share a total of 100 keys to communicate securely, because there's one encryption and 100 decryption. So as explained earlier, symmetric encryption would require around 5,000, whereas this one just uses one for each of the users, right? So there are many programs available for symmetric encryption. We'll focus on GNU Privacy Guard and OpenSSL project. GNU Privacy Guard looks like this. So this is the actual command line to be able to encrypt a file using GPG, and where the cipher is the name of the encryption algorithm right here. And you can check supported ciphers using the GPG version, and the encrypted file will be saved as message.txt. And the default output is in the binary OpenPGP pretty good privacy format. However, if you prefer to create an AC armored output, which can then be opened in any text editor, you should add the option armor. For example, before symmetric, you add armor, and the rest of it looks pretty much the same, cipher algo, and then the cipher itself, which would be, AES 256, for example, and then you have the output message. So you can decrypt using the following command. So this is how we encrypt, and then so you do GPG output the original message TXT, and then decrypt the message GPG. And so we have OpenSSL project, and that is encrypted this way. You have OpenSSL, and I've used OpenSSL in previous rooms to create an actual certificate for us, an SSL certificate. So OpenSSL AES 256 CBC is the algorithm. EIN message TXT out encrypted message, right? IN was probably in and then out. So the input is the message, the output is the encrypted message, and then we can decrypt the resulting file following the using this following command: OpenSSL, same algorithm. And then so this is, now I understand that E stands for encrypt, D stands for decrypt, and then you input the encrypted message, and then you output the original message TXT. To make it more secure and resilient against brute force, we can add PBKDF2 to use password-based key derivation function 2. Moreover, we can specify the number of iterations on the password to derive the encryption using iteration and then the number. To iterate 10,000 times, the previous command would become the same at the beginning. Then you just add the password-based key derivation function. You iterate 10,000 times and you encrypt, and you do the same thing later. And then if you wanted to decrypt it, do the same thing, and you just got to make sure that you do the password-based key derivation function, iterate 10,000 times, use decrypt as the flag, and then the encrypted message and the original message. In the following questions, we're going to use GPG and OpenSSL on the attack box to carry out symmetric encryption. The necessary files for this are inside of this place, so the zip file can also be used to tackle those questions. So I'm going to actually open up the attack box because I didn't know I had to open it. So I'm going to start the attack box, and then that's going to take a couple of minutes to load, and then once that loads, we will begin answering these questions here. Oh, right, so our attack box has loaded, and I went into the terminal and CD'd into here. So I changed directory into the directory that they told us where the stuff is. So this is what's inside here. There we go. So we have 3 files right here, quote 1, quote 2, and quote 3. So these 2 are the TXT files that I think we're going to end up decrypting, and I think this is something, well, we'll see actually. So yeah, we are decrypting all of them, but we're just using different versions of these commands, I believe. So for the first one, is decrypt quote 1 using encrypted using AES 256, and then this is our key, and then using GPG, what is the third word in the file. So I need to first find out how I can designate a key, because let me see. All right, for this one, I believe we are going to end up using GPG to go ahead and figure this out. Actually, so let's run GPG version to see if we have the right version of GPG, and let's see the ciphers that we can use with it. And it says that we can use the AES cipher, so that should be fine, and AES 256 also, so that should be fine. Okay, so now we can try to use this command that they have here. So we have GPG, and we're going to do output, which is going to be basically, we'll do quote 1 decrypt, we'll call it that, and I'll do txt, and then we have the decrypt itself, which is going to be oh crap, I need to first get the, actually if I just do quote 01 and do tab, there you go, that worked. Okay, so that's what we're going to do, and we're going to press enter here, and then look at that. So it's asking us for a passphrase, and I think that's where our key comes in right here. So we're going to take this thing. Can I move this or no? So I'm just going to see if I can, I'll just type it, who cares. So S exclamation KR capital 3 T capital 55, enter. All right, that completed. So now if I do an ls here, I should have a new file, and quote 1 decrypt, there it is. So cat quote 1 decrypt, and that should be my file. There we go. Do not waste time idling or thinking after you have set your goals. Miyamoto Musashi. There's so many good quotes inside of this room. So it says, what is the third word in the file? So the third word is waste in this case. And there we go, just like that, we got it, nice. All right, for quote 2, we're going to be using OpenSSL, and the command is right on the screen right there. So AES 256 CBC, and then we're going to do -D for decrypt. The input is going to be our quote 02 file, and then we're going to do an output, which will be our quote to decrypt.txt. Press enter. Oh, I see what I did wrong there. I did not put a dash in front of in. So I'm going to redo that real quick, and I'm just going to go and put a dash in front of in, and that should be fine. So if I just do this right here and press enter, that should be good. Okay, there we go. There's the password prompt. So now we're going to type same password, S, and then KR3T55. Deprecated key would be fine. Does that mean that it didn't work? No, it did work. Okay, great. So cat quote to decrypt, and let's see if that works. It does. And the true science of martial arts means practicing them in such a way that they will be useful at any time, and to teach them in such a way that they will be useful in all things. Miyamoto Musashi. I freaking love this guy. I don't know what I think he's the one that wrote the 5 Rings or something. He's like the greatest samurai in the world or something like that. So third word here is science. And finally, decrypt the quote 3 file, encrypted using Camellia 256 with the key using GPG. So let us now do that one. And I think it's going to be a very similar command to the one that we just saw. And I will, I mean, I guess I could check Camellia, or check to see if Camellia is already in there, but I think we already have it. So let's see. I could just scroll up technically if this thing actually works. Okay, there we go, I see it. There is Camellia 256. This thing's slow as hell. Okay, so let us, it's also because I have like 100 browsers open on my second monitor. So I can't really blame the computer for me going crazy with my RAM usage and my internet usage. So we're doing GPG again. So let's scroll here. And there is the decrypt file. So there we go. So decrypt first is going to be output. And then we'll have quote 3 decrypt.txt. There we go. And then we have decrypt quote 03 txt gpg. Enter. I misspelled output. How do you misspell output, bro? Let's go fix that real quick so that we can actually do something. And there is our password prompt. So skr3t55, enter. Cool beans. And so now let's just cat quote 3 decrypt onto the screen. And we are looking for the third word in the file. So same thing, third word. And in this, it says, you must understand that there is more than one path to the top of the mountain. I feel like these quotes are just meant for me right now. This is amazing. I love this so much. I want to save all of these quotes. I'm literally actually going to save all of these quotes because this is speaking to my heart right now. And I just need these quotes in my life. All right, now that I have saved all of my quotes, I am now going to move on. We're going to move on from symmetric encryption to asymmetric encryption. All right, so asymmetric encryption. Here we go. Symmetric encryption requires the users to find a secure channel to exchange keys. By secure channel, we're mainly concerned with confidentiality and integrity. In other words, we need a channel where no third party can eavesdrop and read the traffic, so no man in the middle, right? Moreover, no one can change the sent messages and the data. Asymmetric makes it possible to exchange encrypted messages without a secure channel. We just need a reliable channel, meaning that we're mainly concerned with the integrity and not necessarily confidentiality. When using asymmetric encryption, we would generate a key pair, a public and a private key. The public key is with the world, and they can use it to view something, or with the people who want to communicate with us securely. The private key must be saved securely. So if people find the private key, they kind of get access to the kingdom, so to speak, and no one gets to access it. So it's not feasible to derive the private key despite the knowledge of the public key. How does this work? So if Alice encrypts a message using Bob's public key, it can be decrypted only using Bob's private key. Reversely, if Bob encrypts a message using his private key, it can only be decrypted using his public key. So confidentiality. Alice wants to ensure confidentiality in her communication with Bob. She encrypts the message with Bob's public key, and Bob decrypts it using his private key. Bob's public key is expected to be published on a public database or on his website, for instance. And so a common version of this is the SSL ticket, the certificate that secures a website and turns it from HTTP to HTTPS. And that's like a really well-known one. So if you click on this right here, and if we go over here and it says connection is secure for TryHackMe, and then we go look at where is it? Click on connection is secure, and then it shows us the certificate is valid, and we look at the certificate. This is basically what they're talking about here. So this is the public key of the certificate, right? And then that's the actual certificate ID or hash. And then the website itself has a private key, and they're not going to give us the private key, but we get our own public key. And so the public key allows us to access this website without any issues and integrity, so on and so forth. So that's like a very common version, like a very well-known version that you may not have known was an asymmetric type of a key, but that's what it is. Asymmetric encryption in this case is the HTTPS SSL TLS certificate that websites use. So Alice uses a plain text, goes through the encryption with Bob's public key, and it turns into ciphertext, and it gets sent into the web. The ciphertext goes over here, and Bob's private key decrypts it, and he gets the plain text message. When Bob wants to reply, he uses plain text, Alice's public key here, and then it encrypts everything, and then Alice uses her private key to decrypt it. So in other words, it becomes easy to communicate with Alice and Bob while ensuring the confidentiality of the messages. The only requirement is that all parties have their public keys available for interested senders. In practice, symmetric encryption algorithms allow faster operations than asymmetric. Therefore, we will cover that later, how we can use that best of both worlds. Integrity, authenticity, and non-repudiation. Beyond confidentiality, asymmetric encryption can solve integrity, authenticity, and non-repudiation. Let's say that Bob wants to make a statement and wants everyone to be able to confirm that his statement indeed came from him. Bob needs to encrypt the message using his private key. The recipients can decrypt it using Bob's public key. If the message decrypts successfully with Bob's public key, it means that the message was actually using Bob's private key because it's a key pair, right? In practice, he would encrypt a hash of the original message, and we'll elaborate that later. Being decrypted successfully using Bob's public key leads to a few interesting conclusions. First, the message was not altered across the way, and this proves integrity of the message. Second, knowing that no one has access to Bob's private key, we can be sure that this message did indeed come from Bob, and it's the authenticity. And because no one other than Bob has access to his private key, Bob cannot deny that he sent the message. So that ensures non-repudiation. So plain text, he uses his private key and it gets encrypted, and then we use his public key to decrypt the message and access it. So this is one of those things where, like, when you look at Google as a website or Gmail as a website, and to make sure that that's actually their website, you can check their certificate and you see, oh, this is actually Gmail. But a lot of times, or sometimes when it's a fake website, then you will notice that either there will be a big error message onto the screen that says, hey, this is, be cautious proceeding forward because this website is not secure. And you think you're going to a very well-known website when they've created some kind of a dummy domain or an identical, not an identical domain, but an impersonating type of a domain to try to do that. So it's very important to understand that. RSA got its name from the inventors, Rivest, Shamir, and Edelman, and it works as follows. You have two random prime numbers, P and Q, so calculate N equals P times Q. And the two integers, E and D, such as E times D equals 1 modified not N, where not N equals N. Yeah, this is very, very, I don't understand what I just read. I'm just reading the algorithm. But this step lets us generate the public key and the private key. So NE is the public key and ND would be the private key. The sender can encrypt the value X by calculating Y equals X to the power of E mod N, so the modulus. The recipient can decrypt Y by calculating X, so on and so forth. This step explains why we put a restriction on the choice of E and D. As if I understand the fucking explanation here. I have literally no bullshit. I have no idea what any of that means. This is all just jargon to me. Might as well be a different language. But I'll take their word for it, okay? Don't worry if the above mathematical equation looks too complicated, okay? You don't need mathematics to be able to use RSA, and it's readily available via programs and programming libraries. RSA security relies on factorization being a hard problem. It is easy to multiply P by Q. However, it's time-consuming to find P and Q given N. Moreover, for this to be secure, P and Q should be pretty large numbers, for example, each being 1,024 bits. And that's a number of more than 300 digits, by the way. And it's important to note that RSA relies on secure random number generation, as with other asymmetric encryption algorithms. If an adversary can guess P and Q, the whole system would be considered insecure. Let's consider the following practical example. Bob chooses two prime numbers, P equals 157, Q is 199. He calculates N, which is 31,243, multiplying these two to each other, with this part of the equation equaling 31,243 minus 157 minus 199 plus 1. This is what the number comes out. And he elects E as 163, D as 379, where E times D equals 163 times 379, 61,777, and 61,777 modulus 30,888. And the public key is 31,243,163, and the private key is 31,243,379. Kind of see the pattern here, okay? Let's say that the value to encrypt is x equals 13, and then Alice would calculate and send y equals x to the power of e mod n equals 13 to the power of 163. So y to the power of e. In this case, E is 163, and where's Y? Do we have Y here? We don't have Y. So E is 163, so Y equals X to the power of E, and in that case, it would be 13 to the power of 163 modified into 31,243 equals 16,342. Bob will decrypt and receive the value by calculating this. The previous example was to understand the mathematics behind it better, to see real values for P and Q. Let's create a real key pair using a tool such as OpenSSL. So this is the command: OpenSSL gen RSA, generate RSA, output the private key PEM file based on a 2048 bit, and then OpenSSL RSA in private key PEM, pub out, and then out public key PEM, and then it starts writing, and this becomes the public key. And then you can do OpenSSL RSA in the private key PEM, and then the text, and then no out, and then this ends up being the modulus version of it. Private exponent, prime 1, prime 2. And so we executed three commands: OpenSSL, gen RSA. With OpenSSL, we use gen RSA to generate an RSA private key. Using out, we specified the resulting private key saved as a PEM file. We added 2048 to specify a key size of 2048 bits. And then RSA in the PEM file, pub out, and then out the key public key PEM file. So we did the private key PEM, and then now we're generating the public key PEM. Using OpenSSL, same RSA algorithm. And then we specify that we want to get the public key using pub out. So we want to get a public key out. Finally, we set the private key as the input, which was our private key PEM. And then we got a public key PEM output. And then OpenSSL RSA in the private key, text, and then no out. So we're curious to see the real RSA variable. So we use text and no out. And prime 1, prime 2, modulus, and public exponent are the respective values of P, Q, N, and E, and D. So public exponent and private exponent. These are the respective values of these variables right here. If we already have the recipient's public key, we can encrypt it with the command OpenSSL pkey utility encrypt input plain text, output ciphertext in key, public key PEM file, and then pub in. So we want to use the public key in. And then the recipient can decrypt it by using pkey utility, same thing. Decrypt instead. In is going to be the ciphertext, which is right here. In key is going to be the private key, which was, they have it, right? They need to have that. And then the out file is going to be the decrypted text. And then that's what that looks like. So on the attack box, we can find this in our task 3, which I've already opened up. And we can retrieve the ciphertext message sent to Bob from Alice, and find the key that we need in the same folder. What is the first word of the original plain text? So All right, here's our working files inside of the task3 directory, and we have ciphertext, private key from Bob, public key for Alex, and public key for Bob. And so right here it says decrypt with Bob's private key. So we're going to be using decrypt as our message here. So it's going to end up being this command from what I understand. So let's try to duplicate that command using the files that we have here. I think that worked. I didn't get any error messages, and now I have a decrypted txt. So decrypted txt. Let's see what that actually reads. It did work. Great. So now it says, what is the first word of the original plain text? And another powerful quote for Miyamoto Musashi. Perception is strong and sight weak. In strategy, it is important to see distant things as if they were close, and to take a distanced view of close things. That is deep as hell. This guy is my new favorite author slash hero slash strategist. I am freaking blown away by this. So now we have perception being our first word here. All right, take a look at Bob's private RSA key. What is the last byte of P? So P is prime 1, and the answer should be 2 hexadecimal digits. And the way that we looked at that was this command right here. So we're looking at this, open RSA in private key, and then text yada yada yada. So we want to look at his private key, open SSL, RSA in, it's going to be Bob private, or no, private key Bob, and then text no out, and that's going to give us our info. And then we're looking at P, which is going to be prime 1. There it is. And I passed it already. There we go. So E7 is going to be prime 1. E7. And let's look at his private RSA key. What is the last byte of Q? And Q is prime 2. So right here, and easy does it, and that one says 27. So there's that. And there we go, we got it. So just like that, we were able to wrap up asymmetric encryption. So let's look at the Diffie-Hellman Key Exchange. Alice and Bob can communicate over an insecure channel. By insecure, we mean that there are eavesdroppers who can read the messages exchanged on this channel. So how can they agree on a secret key in an environment like that? One way would be to use the Diffie-Hellman Key Exchange. It's an asymmetric encryption algorithm. It allows the exchange of a secret over a public channel. We'll skip the modular arithmetic background, thank God, and provide a simple numeric example. We will need 2 mathematical operators or operations, power and modulus. So xp, in this case, x raised to the power of p. X is multiplied by itself, p times. Furthermore, x modulus m, which is x modulus m, is the remainder of the division of x by m. Okay, that's what that means. Okay, I knew that. Jeez, all right. Alice and Bob agree on Q and G. For this to work, Q should be a prime number and G is the number smaller than Q that satisfies a certain condition. In modular arithmetic, G is a generator. In this example, we take Q equals 29 and G equals 3. Alice chooses a random number, A smaller than Q. She calculates A equals G to the power of A modulus Q. The number A must be kept a secret. However, A is sent to Bob. Let's say that Alice picks the number A equals 13 and calculates A 3 to the power of 13 modulus 29 equals 19 and sends it to Bob. Bob picks a random number B smaller than Q. He calculates B equals G to the power of B modulus Q. Bob must keep B a secret, the lowercase b, not the uppercase b. And however, he sends B, the uppercase B, to Alice. Let's consider the case where Bob chooses the number B equals 15, lowercase equals 15, and calculates B equals 3 to the power of 15 modulus 29 equals 26. He proceeds to send it to Alice. Alice receives B and calculates key B to the power of A modulus Q. And then Bob receives A, calculates key A to the power of B modulus Q. And they both end up being 29 equals 10 essentially. So, or not 29 equals 10, is 26 to the power of 13 modulus 29 equals 10. 19 to the power of 15 modulus 29 equals 10. So we can see that they reach the same key. Although an eavesdropper has learned the values of Q, G, A, and B, they won't be able to calculate the secret key that Alice and Bob have exchanged. The above examples are summarized in the figure below. If you want to, pause this and go through this, you're more than welcome to. But I'm pretty much done with arithmetic right now. Although the numbers we have chosen make it easy to find A and B, even without using a computer, real-world examples would set a queue of 256 bits in length. In decimal numbers, that's 115 with 75 zeros to its right. I don't know how to read that either, but I was told to read it as 115 quadrovigintillion. Yikes. Such a large queue will make it infeasible to find A or B despite knowledge of Q, G, A, and B. They're talking about the lowercase a or b. So it's infeasible to find lowercase a or b even though you know the rest of the variables. So we're going to look at the actual Diffie-Hellman parameters. We can use OpenSSL to generate them. We need to specify the option DH_param to indicate that we want to generate the Diffie-Hellman parameters along with the specified size in bits, such as 248, 2048, or 4096. In the console output, we can view the prime number P, uppercase P, and the generator G using the command OpenSSL DH_param in DH_param's PEM text no out. This is similar to what we did in the RSA private key. So this was the first command where they used the 2048, I think, to, oh, I see. Oh, no, so excuse me. Yeah, this is the first command, and then this is the second command. There you go. So OpenSSL DH_param output is going to be the PEM file using 2048 bits. OpenSSL DH_param input is going to be the PEM file, and then we want to get the text reading of that, the text output of that. The key exchange algorithm Diffie-Hellman allows two parties to agree on a secret over an insecure channel. However, the discussed key exchange is prone to a man-in-the-middle attack. An attacker might reply to Alice pretending to be Bob and reply to Bob pretending to be Alice, and we'll discuss the solution later. So on the attack box, you can find the directory for task 4. Alternatively, we can use that. So a set of Diffie-Hellman parameters can be found in the PEM file. What is the size of the prime number in bits? So let's look at that. Okay, so here is our PEM file. So let's do this little command here, OpenSSL. And there is our info, and we're looking for the size of the prime number in bits. So let's see if I can find that here. And it's right there. Oh, damn it, it went by again. There we go, 4096. And what is the prime number's last byte, which is the least significant byte, and it is this thing down here, which is 4F. And there we go, we got it. So this one was a fairly short one. So Diffie-Hellman Key Exchange is done. Let's go into hashing. Hashing, a cryptographic hash function, is an algorithm that takes the data of arbitrary size as its input and returns a fixed size value. So we've talked about this a lot, so I'm not going to spend too much time on this. Just in case you need to, you can kind of read through this if you want to. But it basically creates, and there's a lot of different algorithms. So there's the MD5. I think there's different versions of the MD5, or not MD5, but different versions of MD. And then there's the SHA, and then SHA has SHA-1, SHA-128, SHA-256, so on and so forth. And in the SHA-256 sum calculates the 256 secure hash algorithm message digest, and as the name indicates, it returns a checksum size of 256, which is 32 bytes, and it's usually written using hexadecimal digits, and hexadecimal digit represents 4 bits. The 256 checksum can be represented as 64 hexadecimal digits, so it's going to return a 64-digit checksum. In the output below, we calculate the hash values for 3 different files of varying sizes: 4 bytes, 275 megabytes, and 5.2 gigabytes. Using this to calculate the message digest for each of the 3 files, we get 3 completely different values, and it should be that way. It's worth stressing that the length of the resulting message digest or chunk sum is then the same, and it doesn't matter how big or small the actual file is, and it'll change if even if literally a dot is added to the context of that file, or if the name of the file changes by 1 character, the hash value changes completely. So the 4-byte file abc.txt and the 5.2 gigabyte file resulted in message digest of equal length, independent of the actual size file itself. So we do ls to see what the files are, and then these are the files right here, and it gives us the sizes of the files. And so you just run it, right? SHA-256 sum for everybody. So if you just do the asterisk command, it just does everything inside of the directory that you're at. And so you see ABC has a different value, DBN has a different value, and Win11 has a different value, but they're all the same size. So these are all 64 characters, right? So that's what's kind of important to take away from this. So why would we need such a function, right? Storing passwords, instead of storing passwords in plain text, a hash of the password is stored. Consequently, if a data breach occurs, the attacker will get a list of password hashes instead of the original passwords, and passwords are also salted, and we'll talk about that in a little bit. Detecting modifications. Any minor modification to the original file would lead to a drastic change in hash value, and this is done a lot in forensics for chain of custody to try to see whether or not digital forensic files have been changed in the chain of custody between transferring from place to place, and if the hash value has changed, then you know that the file has been changed. In the following terminal output, we have 2 files, text1, text2, and they're mostly identical except for literally 1 bit big difference being different. The letters T and T are different sizes, and even though you did that, you have different hash values, right? So this pretty kind of important to understand here. When you look at the hexadecimal, what's inside of these things, there's literally only one thing that's different. Everything else is exactly the same. There's one thing that's different, which is the first letter of TryHackMe. One of them is capitalized, the other one's lowercase. But being that, they get completely different hash values. And this is important to understand. That's what hashing really means. These are common. These are very common. So you have SHA-224, 256, 384, 512, and then RIPE MD 160. They're meant to be the most secure. But you can still, there's still databases like CrackStation that can reverse the hash value of a password because they have a really large database of hashes collected, and so they have clear text versions of a lot of different hashes. So it could technically be secure, but if the password itself is a weak password and it exists in a lot of these password dictionaries, then most likely you'll get decrypted. MD5 is an old one. SHA-1 is an old version of SHA. They're cryptographically broken. By broken meaning that it's possible to generate a different file with the same checksum as a given file because the amount of digits that comes out is a shorter amount. And so since it's a smaller amount of digits that comes out, it is possible that those digits can be used for multiple files because there are literally trillions of files by now. So there could be something called a hash collision if you use those things. In other words, an attacker can create a new message with a given checksum by detecting the file or message tampering, and detecting a file or message tampering won't be possible. Then we have HMAC, which is hash-based message authentication code, and a message authentication code is a message authentication code that uses a cryptographic key in addition to a hash function. So it's a little bit secure, or more secure. According to RFC 2104, HMAC needs a secret key, an inner pad, also called an iPad, and an outer pad, considered an OPAD. And the secret key, and then there's both of these are the constant strings, and it uses 0.36 repeated B times for the iPad. The value of B depends on the chosen hash function, and then it does 0 times 5C or 0x5C repeated B times for the OPAD. And calculating HMAC follows these rules. Append zeros to the key and make it of the length of B to make sure that the length matches the actual iPad. Using bitwise exclusive OR, which is XOR, represented by calculate key iPad. Append the message to XOR. Output from step 2, apply the hash function to the resulting stream of bytes using XOR calculate key and OPAD. Append the hash function output into this, and then apply the hash function to the resulting stream in step 6. And again, this is over my head, okay? So if you've never done anything with hash values and things like that, I don't expect you to understand this. They're just saying this so that you can understand the complexity of these things and understand why these things are used for security and encryption. You know what I mean? So the figure above represents the steps expressed in the following formula. And then to calculate HMAC on a Linux system, we can use any of the available tools. HMAC 256, SHA-224 HMAC, 256, 384, 512 HMAC. So these are different connections to the SHA algorithm, as you can see. And then the secret keys added after the option key. And we see an example below. So HMAC 256, and then you have, this is the key itself. And then you have message text, key, message text, and then SHA-256 HMAC, message text, key, message text, key. So we're going to use task 5 to answer these questions. And let's first go into task 5. All right, so here are the files that are inside task 5's folder. And so the first one is, what is the SHA-256 checksum of order.json? So very simple. We're going to literally just do SHA-256 sum and then order.json. That's it. And there is our hash value. And we're going to copy that. And that's it. This is fairly easy. Hash values are kind of easy to mess with. So open the file JSON and change the amount from 1000 to 9000, and what should be the new hash value. And this is, by the way, hash values stay the same across all time as long as the file isn't altered. And so if you do alter it in the same way, it'll also stay the same hash value. So that's a good thing to know as well. So we're going to, what does it say? Open the file, order.json. And then from here, we're going to change the amount from 1000 to 9000. There we go. And then we're going to save it, exit out, go right there. And now we are going to do the same command, literally SHA-256 sum, order JSON. And look at that, the hash value completely changed. Copy, and there you go. Voila. By the way, I mentioned in the very first video of this series in the Security Engineer that, you know, there's a prerequisite room that was covered, which was the pre-security room. And inside of that, or the pre-security pathway actually, inside of the pre-security pathway, there was a bunch of things that you need to know as a prerequisite to be able to go through these things. And one of them is Linux fundamentals. And inside of Linux fundamentals, there's tools like Nano that you need to know how to use. And I didn't explain what I just did by opening Nano and then modifying and then saving the file, so on and so forth. So I'm assuming that you know how to do that already. And if you don't, I do recommend you either go and Google how to use Nano. There's a lot of different videos that I've done that cover Nano in it. Unfortunately, they're not time-stamped or in the descriptions of any of the videos, so you can't really find them by doing a search. So I do recommend that you learn some basics about Linux fundamentals and how to use Nano. There are some Linux fundamentals rooms though, videos on this channel, so you can at least use those videos to learn about the various tools and command line etiquette of Linux. And yeah, so anyways, using SHA-256 and the key, this one, what is the HMAC of order.txt? So what we're going to do is SHA-256 HMAC, and then the file that we're looking at is order.txt, and then what we're going to do is we're going to put a key at the end of it, and that key is going to be 3RFDFZ82. SHA-256 HMAC not found. What does that mean? What? Okay, that one worked. For whatever reason, SHA-256 HMAC does not exist on this machine. So instead I used HMAC 256, and then I put the key right after it, and then the txt file. So let's see if this is actually the correct hash value that we're looking for here. Hopefully it is. Okay, that worked. Very good. All right, so we got it. And that was our task on hashing. So let us move to PKI and SSL TLS. PKI and SSL TLS. Let's see. We got a key exchange such as the Diffie-Hellman Key Exchange allows us to agree on a secret key under the eyes and ears of eavesdroppers. This key can be used with a symmetric encryption algorithm to ensure confidential communication. However, the key exchange we described earlier is not immune to MITM, man in the middle. The reason that Alice has no way of ensuring that she's communicating with Bob, and Bob has no way of ensuring that he's communicating with Alice, when exchanging the secret. So consider the figure below. It's an attack against the key exchange explained. So this is the figure, right? And this is our man in the middle guy, right? Mallory, right? Alice and Bob agree on Q and G. Anyone listening in the communication can read those two values, including the attacker, Mallory. As she would normally do, Alice chooses a random variable, calculates, and sends A to Bob. Mallory has been waiting for this step, and she has selected a random variable, M, and calculated the respective M. As soon as Mallory receives A, she sends M to Bob, pretending that she's Alice. Bob receives M, thinking that Alice sent it. Bob has already picked a random variable B and calculated the respective B and sends it to Alice. Similarly, Mallory intercepts, reads it, and sends M to Alice instead. Alice receives M, calculates key. Bob receives M, calculates key. And in that case, Mallory has captured everything, and they have all the information. This susceptibility necessitates some mechanism that would allow us to confirm the other party's identity. This brings us to public key infrastructure. Consider the case where you are browsing website example.org over HTTPS. How can you be confident that you're indeed communicating with example.org servers? In other words, how can you be sure that no man in the middle intercepted the packets and altered them before they reached you? And this is inside the web certificate, as we looked at already in the earlier in the video, right? So when you click on that lock, it actually shows you, and you give a drop down and it gives you the certificate and the details. And then we see our certificate details here for example.org in this case. And they use DigiCert, and then in other words, DigiCert confirms that the thing is valid as long as obviously it hasn't been expired. And then it says that after this date in 2031, it's going to be expired. For a certificate to get signed by an authority, we need to generate certificate signing request and create a certificate and send your public key to be signed by the party. Then send the CSR to the certificate authority. And the purpose for this is for the authority to sign your certificate. The alternative and usually insecure solution would be to self-sign your certificate, and you can always use OpenSSL to actually create a certificate for your website. But again, it's self-signed, not very secure, so on and so forth. So for this to work, the recipient should recognize and trust the CA that signed the certificate. And as we would expect, our browser trusts DigiCert, a signing authority. Otherwise, it would have an issue. It would have issued a security warning saying that, hey, this website is not secure, proceed with caution. Even though you may have a security that you, or not a security, a certificate, excuse me, that you created and uploaded, even though you may have generated one yourself and actually uploaded one, it'll still give a warning message because they don't recognize you as a verified security certificate authority, excuse me. So the certificate manager looks like this, and assured ID root CA, assured ID root G2, G3, CA G2, so on and so forth. So you have it. And you can use OpenSSL to generate a certificate. We already saw that. This is the command to actually use it. Require new is creates a request new, excuse me, creates a new certificate signing request. Save the private key without a passphrase. Generate a new private key. The RSA algorithm and the bit size, and key out where to save the actual key file, and then save the certificate signing request. And so you'll be asked to answer a series of questions as shown in the console below, and this is what it would look like, right? So you run the command, and then you're about to be asked to enter information that will be incorporated to your certificate request, and then you go through the questions. What is the country name, state or province name, locality name, so on and so forth. And once it's ready, you can send it to a certificate authority of your choice to get it signed and ready to use on your server. Once the client, the browser itself, receives the signed certificate, the handshake will actually take place. The secure socket layer handshake will take place, and the purpose would be to agree on the ciphers and the secret key itself. We have just described how PKI applies to the web. A trusted third party is necessary for this, otherwise you'll still get that warning message. And we've created a self-signed certificate for testing purposes. The command will generate the certificate using this command right here. X509 indicates that we want to generate a self-signed certificate. The SHA-256 specifies the digest, and then it will be valid for 1 year as we put 365 days at the end. And so to answer the questions, we need to inspect that certificate file in task 6, and then we can use this to open it and answer some questions here. So let's actually do that. So there are our two files here. And so first we want to do the certificate. So we have a key PEM and a certificate PEM. So we're gonna run this command right here. And I could literally just do, we're looking at which one? Yeah, they want us to actually, literally, I'm just gonna copy paste this. So I'm gonna go here, paste it, and it should just give me, there it goes. I didn't even have to press enter. So let's kind of open this up a little bit. There's the beginning and end of the certificate, and then we have our signature algorithm here, so on and so forth. So first, okay, let me see, what is the size of the public key in bits? So let's go find that real quick. All right, towards the very top, we got it right here. So 4096 is going to be our key size, and then till which year is this valid? So, and it's right here. It's so it's not good before August 11th, 2022, and it's not good after 2039. So that is the year for the expiration. And just like that, we are done. So now we can move on to authenticating with passwords. So how can cryptography help increase passwords? And so public key something something and SSL, we can communicate any server with any server and provide our login credentials while ensuring that no one can read our passwords as they move across the network. This is an example of protecting data in transit. So how we can safeguard passwords in a database, or also known as data at rest, is like this. So you have username, password QWERTY, Bob, password dragon, Charlie, password princess. All of these, by the way, are super weak, and they're inside of a bunch of password dictionaries. So those things, not a good idea. But when you use a hash algorithm, and in this case, this is the MD5 sum of these passwords, it looks like this. So it's no longer a clear text thing. You actually just see hash values, which is safer than having a clear text storage of that. However, the availability of rainbow tables has made this very secure. A rainbow table contains a list of passwords along with their hash value. So CrackStation is one of those websites that just has a bunch of these hash values inside their rainbow table. And the attacker only needs to look up the hash to recover the password. For example, it would be easy to look this up because it exists on CrackStation. So I'm literally going to do this just to show you. We're just going to go to CrackStation. I've used it so frequently. We just paste the hash value for Alice and crack hash, and look at that. It's right there. QWERTY, and it says what? MD5 algorithm. And this specific website has all of these algorithms stored. So SHA-224, 256, 384. So even though SHA-512 is super secure, if your password itself is weak as fuck, then they're going to find it, because a website like CrackStation can easily find it for them. Or you can use John the Ripper or Hydra or a bunch of different websites, softwares, Cain and Abel, just so many different softwares that use a dictionary of passwords like the RockU dictionary, and they'll find your password in there. And there's literally tens of millions of passwords that are stored in free, publicly accessible password dictionaries. And if you have weak passwords, that shit will get found out very quickly. So we need to have more secure approaches to save passwords, and then we add salting to it. So a salt is a random value that we can append to the password before hashing it. An example is this. So this is the hash value of Alice before the salt. This is the hash value of Alice after the salt. So if I went and took this, now let's try to do this, right? So if we go here and see if this one actually exists on CrackStation. I do this, run it, and the password is not found. You see that? Same password hasn't changed. We just added a salt to it. So Bob's hash changes, Charlie's hash changes, and we used hash, password plus salt. Another approach would be hash, and then hash the hash with the hash, you know what I mean? So you just go multiple layers into it. And we used a relatively small salt along with the MT5 hash function, and we could switch to a more secure hash function, meaning SHA-256, and a large salt, and then you really get a really badass password hash, right? Another improvement we can make is to use a key derivation function, such as PBKDF2, password-based key derivation function, and it takes the password and the salt and submits it through a certain number of iterations, like we did earlier, and usually hundreds of thousands. And then you end up getting a really secure freaking password hash. So password storage cheat sheet, if you want to learn more about techniques to store passwords, and this is right here. It's on OWASP's website, or not OWASP's website. Oh, and it is OWASP's website, OWASP.org cheat sheet series, and this is one of their password cheat sheet storage things, which is really badass. I love it. So you're auditing a system, you found MD5 of this. What is the original password? So let's see if that's on CrackStation. Let's see if this is here. Ha! Just like that. So easy. So easy. That didn't even take a freaking 5 seconds, man. That was insane how easy that is. Goodness gracious. The moral of the lesson here is have strong as passwords, so that your passwords are not included in any rainbow tables, so that no matter what dictionary people use, or no matter what websites they use, they can't crack your hash, because your password itself is complicated as hell. So let's go into cryptography and data example, and we will be done with this room. Let's do it. So what happens when we log into a website over HTTPS? A client requests the server's SSL TLS certificate, so client being us. The server, the website, sends the SSL TLS certificate to us, and we confirm that the certificate is valid. The cryptography's role starts with checking the certificate. For a certificate to be valid, it means it's signed by a certificate authority, usually a trusted third party. And then the encrypted hash is appended to that certificate. If a third party is trusted, the client will then use the third party's public key to decrypt the hash and compare it with the certificate's hash. However, if the third party is not recognized, the connection will not proceed automatically, and you'll get a notification that this is insecure. Once the client confirms that the certificate is valid, an SSL TLS handshake is started. The handshake shows, or it allows the client and the server to agree on the secret key and the symmetric encryption algorithm, among other things. From this point, so the handshake allows the client and the server to agree on the secret key and the symmetric algorithm, among other things. There we go. That's the end of that sentence. From this point onward, all the related session communication will be encrypted using symmetric encryption. The final step would be to provide login credentials. The client uses the encrypted SSL TLS session to send them to the server. The server receives the username and password and needs to confirm it, making sure that it actually matches. Following security guidelines, we expect the server to save a hashed version of the password after appending a random salt to it. This way, if the database was breached, the passwords would be very challenging to discover. And that's always a good thing. It's a goal for you to have. It's not good if you're the hacker. It's great if you're the user or the security analyst, right? And so we understand the above scenario, and the purpose is to see how symmetric and asymmetric encryption are used along with hashing to secure communications. And just like that, we have now finished our cryptography introduction. And it felt like I was reading a different language in certain points, and my brain was like, I don't understand what the hell's going on over here. And I just had trouble reading today, which is really not normal for me, so I apologize for that, and I'm hiccuping now. so it's time to move on. The conclusion is not even worth it to read. We just said that cryptography is a vast topic, so we just touched on basic core concepts. So that is it for the introduction to cryptography, which is going to be our day 3, episode 3 of the security engineer pathway. If you're studying for your security engineer, security analyst, pen tester, ethical hacker certifications, any of those things, I encourage you to subscribe and like and turn on the notification bell so that you get notified the next time that a video comes out, because all we talk about on this channel is security and hacking and all that stuff. So this will be directly applicable to your examinations and certifications, but it's also super useful in your day-to-day as a security engineer or a security analyst or a pen tester. You actually will use these things. For example, everything that we did to find the hash value of something, or to create a certificate, or do all that stuff using the command line. You will most likely use these tactics and these strategies in your day-to-day as a security engineer. So it's very useful, and I'm not saying that just to toot my own horn. I think it'll actually be very useful for you. And I started this channel just so I have references to come back to whenever I need to refer back to a certain information. I originally started saving a really big Word document, and it ended up becoming 1,000 pages in a matter of no time at all. And you can't sift and sort through 1,000 pages that easily, because it just becomes harder and harder to load the bigger that the file gets. So I didn't want to deal with that. I just wanted to be able to go to a video, go to the timestamp in the video, and find what I wanted. And so that's why I started this channel. So I'm making it so that it's useful for me, and I know that it's going to be useful for you. So if you can, I recommend it that you like and subscribe, turn on that notification bell, and drop a comment if you have any questions, or if you just want to say hi or whatever. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker / protector. And this was the Introduction to Cryptography room, which is day 3 of our security engineer pathway. Hope you found value from it. Love, peace, and chicken grease. If no one else loves you, Hank loves you. And I will see you in the next room. Later.